Carter, we want to talk today about Ohm's law. We need to introduce a concept to you that you've heard about. It's voltage. So what the heck is voltage? The definition of voltage, it's the amount of potential energy per coulomb of charge. The amount of potential energy, not gravitational potential energy, Jazz and Deep, electric potential energy per coulomb of charge. My analogy for voltage, the one you're going to hear me talk about over and over, I'm going to say that voltage is kind of like height. In the same way that I lift an object up off of the ground to a certain height, I'm giving that object gravitational potential energy because I've done work separating it from the earth. If you separate charges from each other, you've done work in separating the charges. You have created a voltage. Now, it's not a height because it's not measured in meters, but it's the amount of energy per coulomb of charge. In the same way as when you lift something, you do work separating it from the earth. When you separate charges apart from each other, because like charges and unlike charges attract, they want to, I'll use air quotes, fall towards each other. So the units for voltage, well, it's joules per coulomb, but we call this a volt. My physics prof, to distinguish between a lowercase v for velocity and an uppercase V for voltage, always put the little wings, like to make it a capital, like a font serif. It's a habit I'll do quite often. So that's a capital V, that's a lowercase v. Even if you see the V that big, that's probably a lowercase b, unless it's stupid obvious that we're in the context of voltage. Okay? The actual equation for the voltage from a given out by a test charge, it's the potential energy per charge, which I think is on your formula sheet, but I'm not going to be flogging that version of voltage. What I'm going to be flogging, Adam, is the idea that you can think of voltage as analogous to height. Other words for voltage: potential, not potential energy, just potential. You'll often hear electricians talk about a voltage potential. In the same way that you need to have two objects with different gravitational potential energy, different height, for the object to roll down to the next object on its own, current needs two different potentials for current to flow. In other words, if you have a bowling ball sitting on a flat surface, it's not going anywhere until you raise the bowling ball to a height and give it a ramp to roll down. In the same way, if you have charges, they're not going anywhere until you separate them, giving them height voltage. Then charges will flow from a high voltage to a low voltage, from a high potential to a low potential. So what happens inside a voltage source? I'm going to pause the video for just a second. Realize is what happens inside of a voltage source. Work, boy, that's messy. Let's try that again, Mr. Dueck. Work is done separating charges. Through some kind of a chemical reaction going on, you end up with one section of the battery being negative and one section of the battery being positive. Like charges, unlike charges, attract. So the negative electrons want to move this way. Don't write that down, but we prevent them from doing so with some clever chemistry. However, if we attach a wire from here to here, now charges can flow because these electrons are all repelling each other from this area anyways. They'd like to get away and move along. Okay? Because you've done work, you've done energy per coulomb of charge, you've got a voltage. You can kind of think of a battery as lifting charges to a higher potential. The circuit symbol for a voltage source, if we have a wire coming along, The negative side of a battery is a short line. The positive side of a battery is a longer line. That will be one battery. If we had several batteries in succession, they would look like that. But this is just a single battery. Really, I should be calling it a cell. Technically, a cell is a single, what you think of as a battery. A battery is several cells linked together in a battery. So, Jacob, here's my analogy. To understand what's happening in electric circuits, it's helpful to have some kind of a mechanical analogy. The analogy, Alfia, that I'm going to flog to death is the ski hill analogy. I'm going to argue that gravitational potential energy, height, is like voltage. I'm going to argue that in a 6-volt battery that's attached to a circuit, that's like a chairlift where skiers are being lifted up 6 volts high. I know height is not measured in volts, but I'm going to pretend it is. For these skiers to get to the bottom of the chairlift, well, if you get lifted up 100 meters by a chairlift, be stupid obvious, how many skiers how much height do you need to lose to get back to the bottom of the chairlift? If you get lifted up 100 meters, how much? 100, you got to lose 100 meters. In other words, this has to be a voltage drop of 6 volts for this circuit to flow. In other words, in my circuit analogy here, how many volts do I lose going through this resistor exactly? And in fact, I'm going to argue that the ski hill is like a resistor, or a resistor is like a ski hill. Going through it, you're losing energy. You're losing energy per coulomb. So this resistor might be a light bulb. You're losing energy in the form of light and heat. Or it could be something more complicated. But we're pretty good at bleeding that energy off. The charges would arrive back at the bottom depleted, and then they would gain energy going through the voltage source back to 6 volts and continue going through. So I wrote here, the voltage at a point in the circuit is like the height at a certain point on the mountain. The voltage gain in the cell is like the height the skier gains on a chairlift. The voltage drop in the resistor, so this would be the resistor, and that's the symbol for a resistor, jagged lines. That's like the height a skier loses as they move down the ski run. Next page. So potential or voltage is like height. Positive charges want to fall, I'll use air quotes, downhill, the same way a ball wants to roll downhill. Okay, let's talk about current. What would happen if I connect a wire to one side of a battery but not to the other side of the battery? Pretty much nothing. Technically, a couple of charges would move this way, but very rapidly the like charges here would repel these like charges here. No current would flow. So what would happen? We're going to call it a big fat nothing. For current to flow, you need a completed circuit. So what if the wire forms a continuous loop? Well, now you'll have electrons moving through the wire to get to the protons, because unlike charges attract. Now, this particular circuit here is a bit of a problem because voltage is the amount of energy per coulomb. Here, the charges are getting back to the bottom of the chairlift, but they're doing so, they have to lose that energy. Where is that energy going to go? In this previous circuit, the energy would go into the light bulb or the electric motor or whatever resistor there was. Here, the only place the energy can go is into heating up the wires. So here, the energy would go into heating up wires. Is heating up wires a good thing? No, fire bad. In fact, we call this a short circuit. Your stove elements are basically a controlled short circuit. So why is this a better circuit? We're going to turn this into a circuit diagram. So we have a battery, and then the wire goes, and here we have a resistor. There's the circuit version of that picture. Well, this is a better circuit because let's suppose we're gaining 12 volts from the battery. Where is the voltage, the energy per coulomb going? Here's where we're losing 12 volts. If we didn't have that, we'd be losing the 12 volts in the wires, heating up the wires. Now, I'm fibbing a bit. In real life, all wires have some resistance. And so probably if we had a voltmeter, if 12 volts was leaving the battery, we'd probably be detecting maybe 11.7 there. 0.3 volts would be going up into heating the wires up. We're going to pretend that doesn't happen. We're going to pretend our wires are perfect just to keep the math simple. So the key idea is that electrons need a completed circuit for current to flow. If you don't have, turn the page, if you don't have a completed circuit, no current will flow. Put your pencils down, look up.
Ever held onto an electric fence? It hurts.
Anybody here been shocked by an electric fence before? None of you? Okay. Clearly you haven't grown up on farms, some of you. We use electric fences in farms, a fairly safe voltage, but you're going to see people mucking around with electric fences. You should not be mucking around with electric fences. There's always the chance that you have an undiagnosed heart condition. So they're going to be doing some good science, but I would say to you, don't play with electricity.
Farmers use electric fences to keep cattle in and foxes out. If an animal touches the fence, it gets a shock and it runs away. Today, by holding on to this fence designed to shock horses, the brainiacs are going to learn all about electricity. This brainiac is going to touch the fence and get an electric shock. This happens because when he touches the fence, he completes the circuit between the live wire and the ground. The charge goes from the fence itself into the brainiac, through the brainiac's body and down into the ground. Then
Bare feet.
it goes along the ground into the earth stakes.
In fact, if you look close, you can see here's the wires that are connecting the electric fence mechanism to the ground. So there's the completed circuit.
Along the earth wires and back into the unit to complete the circuit. Ouch! And it hurts. Okay, he's getting pretty fed up with that. So what happens if he stands on these polystyrene tiles? Brainiac, touch the fence.
What's going to happen? In fact, this is just the same as earlier when I had the wire just touching the battery on one end. This is the same as birds landing on a wire. This is why they're safe. Now, what really happened is a few charges did flow on him, but very rapidly he matched the same voltage potential as the fence. And so because of that, no charges will flow.
The electricity won't pass through the brainiac's body because it can't go through the polystyrene tiles to the ground to complete the circuit because they're a good insulator, so no shock. Off the tiles, shock. On the tiles, no shock. Off the tiles, shock. Every time this light flashes, there's a charge in the fence.
So in real life, electric fences are never on all the time. They pulse, and you can set the frequency of the pulse once per second, once every half second. Otherwise, Jasmine, your electric bill would be crazy. So especially if you're dealing with cows or farm animals, you have it pulse every second or so. That's enough for the animal to get the message to, oh, I probably don't want to be touching this, but you're reducing your electricity bill. So what does that mean? Well, in theory, it means if you touch an electric fence between pulses, what? You wouldn't get shocked, okay? I grew up on a farm for a few years, and I can remember occasionally accidentally brushing against our electric fence and not getting a shock. And sometimes I did get a shock.
Now, if the brainiac's feet aren't touching the ground when it flashes, he shouldn't get shocked.
So that's your other option, is if you can time your jump just right, you should be okay.
So if he can jump at the right moment, he'll be fine. Brainiac, are you ready? Excellent. On. Look, grab the fence, do it when I say on, be in the air. Here you go. On. Do you have no sense of rhythm?
Theory that would work, but you'd have to nail it perfectly, because if you're a little bit earlier, a little bit late, you're getting shocked.
It's not difficult. You need to work on your timing. Or maybe we need to work on that theory a bit. What's better than shocking a brainiac? Shocking a whole load of them. In you go. All our brainiacs have bare feet, and they're holding hands, as you do.
So what should happen here? They all get shocked?
Now, what will happen when the brainiac at that end grabs the fence? It might just go straight through him to the ground. It might make it all the way to here. Will this brainiac even feel it? Who knows? Let's find out. Brainiac, on the count of 3, grab the fence. 1, 2, 3, go.
The guy on the end didn't get shocked. How come? Yeah, so maybe the first guy, maybe 60% of the current went through him, and then maybe the gal, 30% more, 60 and 30, leaves 10%. Like it goes through the first few people. There might not have been enough charge left for that last guy to feel the shock. He might have received a tiny bit and not noticed it, or he might have received none at all.
Hang on, so you haven't even moved. How far did it get? It got that far.
It got to this now.
Rate that out of 5. 1 to 5, how much did it hurt? 2. 1 to 5, how much did that hurt?
4.
4, right. Change order and let's do it again. Hold hands. On 1. 3, 2, 1, go. You didn't feel it at that end? So it earthed by then.
Although it looked like it went a bit further. Well, yeah, because all of them have different body volumes that can absorb and discharge different amounts of current. So by switching them, it might travel a little bit.
His eyes are still spinning. It seems that the current has never got past this brainiac here. So maybe he has unique insulating properties. Who knows? There's only one way to find out. Stick him on the end. On you go. You go and grab the fence, and on my count. Ready? 3, 2, 1, go! Whoa, now that went further! Where did that end up? Did you feel that? That went as far as that brainiac there. It's killed that brainiac. That's quite impressive. Right, new theory. What happens if we insulate, using these polystyrene tiles, all the brainiacs along the line, apart from the one on the end? Maybe the current will make it all the way. Let's find out. Insulate yourselves, brainiacs.
Now, the first 4 in the line think that because they're insulated, they won't get a shock.
And on my count.
We're going to get a shock or not?
Touch the fence. 3, 2, 1, go. Oh!
Why did they all get a shock? Because that was completing the circuit. The person on the end was touching the ground, completing the circuit. So the charge went through all of them to get to the ground, to get to the complete the circuit.
Oh, yeah. Wow! Well, that really works. Because you were insulated, it earthed here, so for the first time, the current made it all the way to the very end. You all got a shock, and that looked quite severe at this end.
That hurt.
Because they were all holding hands, the current travelled along the line to find the Earth via our uninsulated brainiac, giving everyone along the way a shock.
Oh, yeah. Well, final experiment. What happens if you're insulated as well? Then you're all insulated, OK? So, join hands, please, brainiacs.
So if they're all standing on styrofoam, what'll happen? It's just the same as touching a wire to one end of the battery but not completing the circuit.
And on my count, grab the fence. 3, 2, 1, go. Well, look at that. That's amazing. Nothing because you're all insulated. That's very clever, brainiacs. I hope you've enjoyed learning about electricity. Well done. Good effort, that's what I say. Some people never learn.
Again, entertaining and also informative, but don't play around with electric fences unless you have a defibrillator and an ambulance right nearby just in case. So I've been talking about current, but I haven't defined it. It's defined as the rate of flow of charge in a circuit. Anytime I talk about the rate, what that really means is we're dividing by time. Current is charge, Q, divided by T. And I think I gave you that equation on your formula sheet, I think. Okay. What are the units for current? Well, what's the unit for charge? Coulombs. What's the unit for time? Second. Current is coulombs per second. It's sort of the electric equivalent of velocity, kind of ish. That's so important, though, we call a coulomb per second an amp, symbol capital A. By the way, this also means, because we know that one electron has a charge of 1.6 times 10 to negative 19 coulombs, you can actually figure out how many electrons have passed through a circuit over a given time. Because charge is the number of electrons times the elementary charge, we can say this: if I equals Q over T, and then I stick this in there, I get I equals N times the elementary charge divided by time. Carter, get the N by itself. In fact, I end up getting, if you want to know how many electrons have gone past you in a circuit, that's going to be the current in amps times the time divided by 1.6 times 10 to the negative 19. Which is sometimes kind of fun to do. You'll usually get answers like in the trillion, like a lot of gone by, but it's sometimes kind of fun to do. How many electrons have actually gone by in the last hour in this particular circuit? What's my ski hill analogy for current? If voltage is the height of the chairlift and the height of the ski runs, current is the number of skiers. It's how many skiers are on the ski hill. It's like the flow of skiers up and down a ski hill. Since electrons, we're going to add one restriction, flow at a constant speed, we're going to pretend the skiers are all holding hands and using their skis to adjust their speed so they're all going at the same speed. So, what's happening in a circuit, Chantel? We have electrons flowing this way from the negative to the positive. Problem. I would like to have my circuit go from positive to negative. I'd like to gain energy going through the battery and lose energy going through the resistor. Electrons flow in the wrong direction. So I wrote here, one problem we encounter with my ski hill analogy is that in a circuit, it's the electrons that flow because the protons are not locked inside. The protons are locked inside the nucleus. I couldn't say that very fast. We'd like to, though, be able to say current flows downhill from positive to negative. So here's what we're going to do. We're going to pretend it's the protons that are moving, even though they don't. It's the electrons that move in a chemical reaction. You've all learned this in your science classes. The protons are locked inside the nucleus. But Presley, because a proton and an electron have the same charge, 1.6 times 10 to the negative 19, I'm going to argue that an electron moving one spot to the left is mathematically identical to a proton moving one spot to the right. It's the same thing mathematically. So what we're going to do then is we're going to say the uphill flow of electrons going in the wrong direction, which we don't want, is mathematically equivalent to the downhill flow of protons, which we do want. So what does that mean? We're going to define current to be the direction the positives would move if they could, because it makes the math easier. What we call current is actually the downhill flow of positive charges if they could. Some books will call this conventional current, even though in real life it's the electrons moving. So example 4 says, draw the direction of the electron flow. I'm going to do that in red. Electrons would flow in this direction. They would flow counterclockwise. In my ski hill analogy, I'm not going to write this down, look up. They'll be flowing uphill. Skiers will be going up the ski run and then riding the chairlift down, which is just a tricky way to wrap our brain around it. So instead, we're going to talk about conventional current. Conventional current, Jesse, I'm going to do in blue. And conventional current is from positive downhill through the resistor. In other words, conventional current goes this way, up the ski ramp, up the ski lift, and then that way down the ski run. You gain energy, you lose energy. That makes way more sense. You gain voltage, you lose voltage. This might here make a nice multiple choice question, just saying. So let's talk about Ohm's law and resistance. We've talked about voltage. We've talked about current. Voltage, the height that we're gaining or losing. Current, how many skiers, how fast. What about resistance? Well, every circuit offers some resistance to the flow of charge. The circuit symbol for a resistor is a series of short wavy lines like that. What is this resistance, Chantal? It's due to, I'll call it electrical friction. As the electrons are moving through the circuit, we're pretending it's the protons moving, they're bumping into molecules. And in the same way as when you rub your hands together, that generates heat, electrons moving through a circuit will generate electric friction. They'll generate heat. Heat is energy. So the energy lost by the electrons heats up the material they're passing through, and we're pretty clever at bleeding that heat off and using it to do useful work. So because you're losing energy, that means you're losing voltage, because voltage is energy per coulomb. In other words, let's suppose right here I was at 8 volts. The current is moving to the right. I go through a resistor, and later on you measure this to be 3 volts. How many volts did I lose going through the resistor? Be stupid obvious. Yeah. Now, I wrote -5. Very shortly, we're going to say, because you're always losing voltage in a resistor, we're going to get lazy and not bother writing the negative. We're just going to call it a voltage drop, and we know we're losing energy. Just letting you know. So the amount of flow through the circuit, current, depends on resistance and voltage. So high resistance, that's going to be a really narrow ski run, just a trail. If it's just a trail, can you get more skiers or fewer skiers on that run if it's just a thin trail? Okay, Carter, you're awake. I see a bunch of you zoning out. This is crucial stuff. If it's a thin trail, can you get more skiers on that run or fewer skiers on that run? Be stupid up. If it's a high resistance, bigger current or smaller current? Yep. High resistance, current gets smaller. Low resistance, Anderson, you can think of it as a wide open ski run, maybe 300 meters wide. Can you get more skiers on there or less skiers on there? Low resistance, current goes up. Notice those are opposite. Big resistance, small current. Small resistance, big current. That means in our equation, the R is going to be on the bottom compared to the I. What about voltage? Now, what if I said voltage is? It's height. What's more popular, a really tall ski run or a really short bunny run? Okay, large voltage drop, bigger current, low voltage drop, smaller current. Notice, Adam, these two match. Big voltage, big current, small voltage, small current means the V is going to be on the top. As an equation, we have this. Current is voltage divided by resistance. That's Ohm's law. Although Ohm's law is usually written as V equals I times R. I think I gave you that on your formula sheet. In fact, I know I did, but trust me, this is one worth memorizing. V equals I times R. Oh, also I equals V over R. And R equals V over I. Just getting whichever you want by itself. Okay. going to be technical here. Technically, because we're losing voltage going through a resistor, technically this should be a change in, don't add that, it should be a change in voltage, because in the same way to measure height, Adam, you have to measure the bottom and then the top. You need to know where you started from. You're always going top minus bottom to measure height. To measure voltage, you're always going higher voltage minus lower voltage. If any of you have ever used a voltmeter, they always have two probes. You touch one to one area, touch one to the other area. It's measuring the potential difference. Yep. I did on the formula sheet, but we're going to get really, really lazy. In the same way, time is always a change in, voltage is always a change in, the notation is cumbersome, and so we're not going to put a delta in front of it all the time. Yeah. What are the units for resistance? Ohms. 1 ohm is 1 volt per amp. What's the symbol, the abbrev for ohms? Why don't we use a capital letter O as our abbrev for ohms? Why don't we use that? Looks too much like a 0. We thought of that. So what we use is the Greek letter omega, which is that. Looks kind of like a mouse hole in a wall from your morning cartoons growing up. Okay. Good conductors have small resistance. Insulators have high resistance. You don't need to memorize this next chart. I just like to give you some ideas of what's really big and really small. What I've done is I've got 6 different resistors here, and I've got 6 different resistances as numbers here. Let's see if we can do a little clever mixing and matching. I notice one of the resistors is infinite. Of these, which of these just does not conduct electricity well at all? And if you don't know, I'll tell you, but glass is a very good insulator. If you see the big metal power lines, you know, the ones that go over the mountains, those ones, where the lines touch the metal towers, there's these black discs. Those are ceramic glass. Basically, very good insulators, nearly infinite resistance. Otherwise, the electricity would be going through the metal into the ground, which would be a bad thing. Okay, so a piece of glass has a nearly infinite resistance. I'll put the symbol for infinity and 8 on its side, and I'll cross that out. Let's go in the opposite direction. Of the remaining 5 items, which of these do you think has the smallest resistance? Your hint is, yeah, your hint is this is what we use to make all of our circuits. Copper. Because we don't want to be losing, remember, voltage is energy per coulomb. We don't want to be losing energy to heating up wires. So copper has a resistance of about 0.1 ohms. Silver has even smaller resistance. Gold has even less resistance. Why don't we make all of our circuits out of gold? Okay. But you know who does make their circuits out of gold? NASA. If you ever see a picture of a NASA probe while they're building it on the Earth, you may notice, what's all that gold foil? It is gold foil. Because for NASA, it's worth getting a few, you know, if you can save yourself 0.1 of an amp, totally worth it. Right? What was the one you suggested? Oh, you know, let's go in the opposite direction. So what's the next highest resistance as a number left? Human skin. Again, thankfully, we're not very conductive. Otherwise, Gibson, you would be getting shocks all the time. You don't realize how often your body is building up a charge and discharging that charge, but it never made it through your skin, never got to your nervous system, so no harm, no foul. Light bulb, we want that actually to be a fairly high resistor. Why? We want it to glow white hot or red hot. So what's a light bulb? Probably around 200 ohms. Electric motor we don't want to run hot. It has a very low resistance. They're usually around anywhere from 5 to 25 ohms. Electric motors don't get very warm. You can run an electric drill full and you can still put your hand on it and not burn your hand. And an average lab resistor, they're usually in the kilo ohm range. So you can get them 1 kilo ohm, 2 kilo ohm, 10 kilo ohm, 100 kilo ohm. Again, you don't need to know that. That was just to give you an idea of what's big or what's small. I should point out resistances in real life as they heat up. Now the electrons and atoms are moving more, electric friction has increased. So in real life, pan which resistances change, we're going to pretend that they don't, just to keep the math simple. What about human skin? Although human skin is a good insulator, typically tens or hundreds of thousands of ohms, it will only protect us up to a certain point. When the voltage exceeds a certain value, when there's a strong enough electric field, your skin will ionize. It will pass an electron to the next skin molecule, to the next skin molecule, to the next skin molecule, the same way lightning can ionize air, passing an electron to the next air molecule, to the next air molecule, to the next air molecule. That's bad because on the inside we're mostly salty water, which is a pretty good conductor. So let's talk about being electrocuted. Once beyond the skin, the danger to our health lies in two effects. If it's a large current, your tissues can heat up because when you rub your hands together, that generates heat. When you send a bunch of electrons, again, we're pretending it's the protons, so I'm going to say protons. When you send a bunch of protons through you, that causes electric friction. That's why people who are electrocuted often are burned. They suffer very severe burns, both on the outside and internally. But also, the current can affect or interrupt your body's electrical nerve impulses. It can lead to muscle contractions or paralysis. When those muscles are your heart, your lungs, and your diaphragm, not good. To get an electric burn, Jazz and Deep, you need a pretty big current to burn your skin. But to cause your heart to fibrillate, you hardly need any current at all. It's only about 100 milliamps, about 0.1 amps. This is actually nicknamed the death current. That's enough to cause your heart muscle to start to twitch irregularly or stop it from beating. And 0.1 amps is not much. How many amps do we get from the outlets here? Let me know. They're capped at 15 amps, which is more than enough to cause you to fibrillate. So be careful when dealing with electricity. Okay, that's also what those electric shock defibrillators do. They try and apply a shock to startle your heart back into its regular rhythm. So voltage is like height. In my ski hill analogy, you gain voltage from a battery chairlift, you lose voltage going through a resistor ski hill. Current is like the number of skiers. Resistance, I just said it, it's like the ski hills. The wider the ski hill, the smaller the resistance. You can fit more skiers. The narrower the ski hill, the hotter the wire will run, the higher the resistance. So high resistance is like a narrow trail. Can't get many skiers on there. Low resistance is like a very wide ski hill. More skiers. Example 7 says find the current in each case. We're about to solve our first circuit. The first thing, because Anderson, you've had me long enough to know I like to write down something mindless as a starting point. First thing I always do when you give me a circuit to analyze is I label downhill. So all of you, here's my battery, here's the positive. Downhill is from positive through the circuit to negative. Draw some arrows in. That's also the direction we're going to move our eyes as we analyze this circuit. Gibson, how many volts did I gain from the battery chairlift? How many volts must I lose through this resistor if I was able to get back down to ground level? Same answer. So let's make a little note here. 6 volts. What's example 7 asking me to find? Ohm's law says V equals I times R. Gibson, get the I by itself. Leave the I where it is. Move the R over. How? Yeah, it's going to be V over R. In the first circuit in the resistor, what's the voltage, Gibson? What's the resistance? They told me in the picture it's a 25 ohm motor. How many amps I can do this in my head. What's a good way to divide by 25? Divide by 100 and times by 4. So 0.06 times, I think it's 0.24, but double check me. Yeah. Now remember, amps is coulombs per second. This battery is losing charge at a rate of 0.24 coulombs per second. Compare that Gibson with this one here. Well, now current is voltage divided by resistance. We still have to get rid of 6 volts, but what's the resistance in the wires only? How many amps are going to flow through this particular current, this particular circuit? Now, a 6-volt battery isn't very big. What'll happen, probably the wires are going to get hot. They may get red hot, hot enough to melt the insulation, but also which of these two batteries is going to last longer? You're only bleeding 0.24 coulombs per second. Here you're bleeding 6,000 coulombs per second. This battery will die really fast. So if you ever have like a small 1.5 volt battery and you connect a wire to either end, you're probably pretty good because that battery doesn't contain much charge. You're going to fry the battery pretty quick. I've got about 30 seconds and the battery will be totally dead. Okay? Versus here, and it's kind of counterintuitive because you might say, well, wait a minute, here we're running a motor. Shouldn't that bleed the battery faster than running nothing at all? No, because the current is going to spike in that. We have a special name for a situation like this, where you have a battery completing a circuit with no resistor in between. We call this a short circuit. A short circuit is when you're connecting two ends of a battery and there's no resistor to bleed off that voltage, so the wires have to do that. It's called short because it has a very small resistance and will experience very large currents. Your stove elements in your house are controlled short circuits. They're designed to be a short circuit. This depends, of course, on the voltage source. If you short circuit a AA cell using lab wires, you'll quickly deplete the cell, but you probably won't even heat the wires up very much. If you short circuit a car battery, because it's got way more coulombs to give out, you'll probably heat up the wires, maybe even melt them. The real danger is short circuiting BC hydro because your power outlets have an unlimited current. Earth can give you as many electrons as it feels. And so again, don't be sticking your tongue into a power outlet or, oh, I saw on YouTube that you can do this. Don't try it. Be very careful around electricity. Okay. Last comment. We've been focusing on DC direct current. The stuff that comes out of power outlets is AC, it's alternating current. It's actually a sine wave that looks like this as a graph. That's because it's way easier to generate or create electric current in alternating form. Everything that I teach you for DC also works for AC. There's a few other things for AC that make it a bit trickier. But so if I'm getting AC from the power outlet, my laptop requires DC. How do I know? Because it runs off of a battery as well. What's going on? If you're using a device that needs direct current, but you're pulling in alternating current, almost always when you plug it in, you'll see there's that rectangular box as part of the plug. You can all see it sitting on the floor, probably right there. That box contains two things. It contains a transformer, not the toy, the electric device that's changing the voltage, because 120 volts for this would fry it. So it's probably stepping down the voltage, and it's probably having an inverter. An inverter basically takes half of the sine wave and inverts it. In fact, who's in pre-calc 12 this year? It actually does the absolute value transformation, but it does it through a physical device, and you get a reasonably straight current. Then there's other things that you can do to get rid of those bumps. The more expensive the inverter, the fewer little bumps you'll have there, and you would do that if you have very, very sensitive electric devices. A good RV, for example, would have a really expensive inverter so that you don't fry out the devices there. Anyways, the power we get coming out of our power lines, it has a frequency of 60 hertz. That means it changes direction 120 times per second. And it has a voltage amplitude. I need to change this. Used to be 113.4 because it was a little dirty, a little messy, but we're much better now. It's pretty much bang on to 120 volts. North America runs on a 120 volt system. Europe runs on a 240 volt system. Do I have any exchange? Where are you from? Yeah. Does Thailand, do you know, is it 120 volts or 240 volt system? I don't know about Thailand. There's pros and cons. Do your plugs look just like the North American plugs, or do they have the round circular prongs that are wider? Okay. So there's pros and cons to both. Europe went 240 volts, and there's probably more advantages to 240 than 120, but there are also some disadvantages. It's why if you go to Europe, you have to buy an adapter for our devices, and you'll see the European plugs look to you strange in the same way our plugs look to them strange. Yeah. I'd have to check that. What's coming into your house is actually 240 volts. So the line that's running from the power line, the telephone pole to your house is carrying 240 volts. It enters the breaker box at 240, then it's split into two 120, but all of you have probably two 240 volt plugs in your house. You have two appliances that move more heat than anything else and therefore require more current and therefore require 240 volts. If you pull them off of the wall, you'll notice it's a round, massive, funky plug. Anybody know which two appliances it is? Yeah. Dryer and stove. Yeah. Stove slash oven. But yeah, yeah. Those two need more voltage. You might have a third one if you have an electric fast charger in your garage. Your folks might have installed a 240 volt outlet there as well. So we do have 240 volt infrastructure. Kind of. It's just all of our devices are pretty much set for 120 volts. What's your homework? Number 2. Number 3. Number 5. Number 6 and number 7. And the take-home quiz.